Hello everyone. Today we're going to be talking about momentum. I'm going to start off by talking about friction. If we took a hockey puck and we slid it on asphalt, it would come to a stop pretty soon. If we took it to a basketball court, we'd find that it would slide a good deal further, keeping its velocity higher for a longer period of time. If then we went to the hockey ring, we'd find that it slides a great deal further than the polished wood, and great deal further than on the concrete. We can show this on a graph by looking at the velocity versus time. And what we see here is that there's a progression of lower and lower friction. And so what ends up is that the velocity stays more or less constant for a longer period of time. Even in the hockey ring, the hockey puck will eventually come to a stop. But this makes us ask a question of what happens if there is no friction at all. So maybe we took that hockey puck into space and gave it some initial velocity. What we would expect is that v is constant. So what happens then when objects interact? And that's going to continue to be the theme of the rest of this lecture. So let's do a thought experiment. So we could take so let's conduct a little experiment. Here we're going to take two standard carts, and by this I just mean that their mass is going to be equal to 1 kilogram. So basically we have two carts, A and B, that have the same mass, and one of the carts is at rest. Let's just say that's B, and the other cart has some velocity, so that's this guy. And so this guy has velocity to this way, and so he's going to collide with B. So we can show this on this plot here, x versus t. So we have this cart moving along. This is going to be the stationary cart. This cart 1 would be our cart B, and this cart 2 would be our cart A. So here A is moving along until there's some collision here. Now cart A is stopped, and cart B starts moving with the same velocity that cart A had. So the final velocity of cart B is going to be the same velocity that cart A started off with. And so if B is not at rest initially, what we find out is that B starts off with some non-zero velocity, and now ends up with whatever velocity the other cart had. So what happens is that as long as these carts have the same mass, in this case they both have 1 kilogram, what happens is that their velocities interchange. So if this guy, cart 2, starts off with some velocity, call this 0.6, then cart 1 after the collision is going to have a velocity of 0.6. And here cart 1 is 0.1, and so this guy afterwards is 0.1. So they end up swapping velocities. And this is if their masses are the same. So now let's see what happens if we collide two objects with different mass. So in this case we have one of these carts that's a double cart, so its a mass is going to be twice as big. And so this guy is going to be at rest. And what we're going to do is collide the other cart into this double cart. So what we see is that the double cart now ends up with some velocity. But now our single cart ends up going backwards. So this is quite a bit different than what we saw when the carts had the same mass. But what you notice here is that these change in velocity that the double cart had, this delta VD. So he's going from some non-zero, from 0 up to the 0.4, so he's going to be 0.4 minus 0 is 0.4 meters per second. That's how fast he's changing. And now the V single, we look at that, and now it goes from minus 0.2 minus our initial, which was 0.6. And now this is 0.8 meters per second. So what we notice here is that these delta V's are related to each other by the difference in the mass. So the smaller, the single cart changes its velocity twice as much as the double cart. In this problem, we're colliding two things on a track. Let's just call this 1. 1 is moving along. It collides with 2. After this collision, we find out that this delta V1 is equal to 3 meters per second, and our delta V2 is equal to 1 meter per second. So recalling that last experiment, we know that if you change your velocity less, you're going to be the more massive guy. So that's our first, most simple observation. So the other term that you may hear instead of massive is greater inertia. And that's going to be an object's tendency not to change its velocity. So the more inertia you have, the harder it is to change that velocity. And this we associate with how massive an object is. So here we have 3 for delta V1, and here we have 1 meter per second for delta V2. So we know that M1, basically we can write a relationship between the two masses. Since M1 changes its velocity a lot more than this guy, we know that V2, that cart 2 must have a greater mass. So the other way we could write this is if we multiply, cross multiply, we're going to end up with 3M1 is going to be equal to M2. Here we have the same expression that we just talked about, this ratio of the masses in comparison to the ratio of the change in velocities. Except here we have one more thing to be mindful of, and that's this minus sign. If we multiply this out like we did before, we're going to get MA delta VA is going to be equal to minus MB delta VB. Now here we have mass is represented by this M, but here we have an important relationship here. We have MV, and so this is where momentum comes into play. Is the momentum of an object is equal to its mass times its velocity. And since M was already taken by mass, which is a more fundamental concept, we have P represent the momentum. So we could write this out as, since this delta tells us that it's V final minus V initial. And writing this out in terms of momentum, we have PA final minus PA initial is equal to negative PB final minus PB initial. So we could rearrange this and get all the initials onto one side. And what we're going to end up with is, here we're going to have PA final plus PB final is going to be equal to PA initial plus PB initial. And this is a bit more intuitive. We here have the momentum, the sum of the momentum of each object after the collision, and the sum of the objects before the collision. So maybe even more fundamental is that the sum of momentum's initial is equal to the sum of our momentum's final. An even more easier way to remember this is that P is conserved. So momentum is always conserved. So let's put this into practice. In problem 4.9, we have a position versus time. Both of them are moving along a straight line, so we can kind of represent this as A is moving this way, and B is moving this way, but not quite as fast. And then after the collision, what's happening? How fast is B moving? How fast is A moving? So the first thing that we were given is that the inertias are different. So this means that MA is not equal to MB. So the first thing that we want to know is which of these two lines belongs to A. So here we have problem 4.9. We have a position versus time graph for collision. We have two bumper cars, A and B. And we know that their inertias are different. So this tells us MA is not equal to MB. Now looking at this graph, I have B moving and A moving, and then there's some collision here. So B is moving at a faster speed, and I know this because the slope in this graph is steeper. So that means that B is actually coming up behind A. And then the collision happens, and now I want to know which of these two lines is A and which is B. The ratio of the masses, A and B, is equal to minus the change in the velocity, B over delta A. So if we guess that this guy was B and this guy was A, what we would end up with is that our change in velocity B is going to be, I don't know, maybe 4, call this 3, call this 1, and call this 0. So it's going to be 3 minus a 4. And then VA is going to be final minus initial, so 0 minus a 1. And so this tells us that both of them are reducing their velocities, the change in velocity. So they started off with some greater velocity, and now they end up with less velocity. So this is not physical. If you plugged it into this up here, you end up with minus delta VB, that would be minus 1. So here we end up with plus 1 over minus 1, so we end up with minus 1 is our ratio of masses. So this is not physical. So let's then work this out the other way. So we know that this cannot be B, so this must be A, and then this must be B. So let's write out our expression again, MA minus delta VB over delta VA. So here, delta VA is going to be final minus initial, so that's 3 minus 1, so that's 2. And delta VB is going to be 0 minus a 4. So that's going to be a minus 4. So if we plug this in up into this expression, we end up with a minus 4, so that's 4 over 2, so we end up with the ratio of masses is a 2. So this tells us that MA is equal to 2MB. So the more massive of these is A. So A must be more massive than B. Let's work out another problem. Here we have 1,000 kilogram car is moving at 10 meters per second. And then runs into the back of this truck. So his mass is 2,000 kilograms, and then his velocity is 0, so he's stationary. Then the 2 gets stuck somehow, so now it's some big wreck. And now we want to know how fast are they moving after the 2 collide. So let's work this out. So it's easier to use the more conceptual conservation of momentum. So our initial momentum, the sum of that must be equal to the sum of our final momentum. So our initial momentum is going to be P for the car plus P for the truck. So the car is 1,000 kilograms times 10 meters per second, and the truck is 0. So this is going to give me 10,000 kilogram meters per second. So then P final is going to be P of the car plus P of the truck. But here they're moving together, so they must have the same velocity. So we could write that as M car V final plus M truck V final. Or we can combine these two to M car plus M truck V final. And now since I know that these two expressions have to be equal to each other, what I end up with is that M car plus M truck, so that's 2,000 plus 1,000, so that's 3,000. V final is going to be equal to 10,000 kilogram meter per second. And so I'm going to end up with is 10,000 over 3,000 meters per second, because the kilograms are going to cancel each other. So this becomes 10/3, or about 3.3 meters per second, is how fast the wreck moves off. Let's work with one final case. So here we have 2 skaters. All right. A and B. And they are at rest, so both of their velocities are 0. Then they push against each other and start moving. So this is our initial case, our final case. If they push against each other, they can't be traveling both in the same direction, so we know that A has to be moving this way and B has to be moving this way. Here we know one more piece of information, and that MA is 45 and MB is 60 kilograms. We also know that A, this 45 kilogram skater, moves off at 0.375. So we know that VA is equal to 0.375 meters per second. And we want to know, what is this VB? So there's one more thing we need to be careful with here, is that how we have this set up is that X is to the right, and we generally say that if you're moving to the right, that's positive. So that means if you're moving to the left, then that must be negative. So VA actually must be negative 0.375. So let's go back to our principles that this momentum is conserved. So let's write out our initial and final momentum. So our initial momentum is going to be MAVA plus MBVB, initial. And since both initial velocities are 0, we end up with 0 initial momentum. So P final is going to give us this 45 times minus 0.375 plus 60 times this VB final. So we know that the initial momentum is equal to the final momentum, so then this 0 must be equal to all of this. So now we can solve it. So let's bring this term over to the other side. So we're going to end up with 60 VF is equal to 45 times 0.375. And now we solve for V final. B is going to give us 45 over 60, 0.375. And I'll write it this way to show you that the ratio of masses is still affecting this final velocity. So we're going to end up with 0.281, and this will be to the right since we got a positive number.